now we're going to switch to the next set of speakers, Fredrik Medley and Andreas Hall, who work for Arriver, or is it Arrivé? That's
well, Arriver.
Arriver. Okay.
What call it?
Yeah. Well, it's nice to finally see Fredrik face to face, because I've known him as a user of BuildBarn for quite some time. So what Fredrik and Andreas are going to talk about is how they invested a significant effort to speed up pre-submit checks on their end for a multi-repository code base that they manage. 25 times is a very interesting number, so I'm really looking forward to all the details. Good luck.
Thank you. Yeah, all right. So I'm Andreas Hall. I am the verification validation architect at Arriver, and
Fredrik Medley, and I'm an algorithm engineer at Arriver, but I've helped Andreas a lot with the integration tests and all our build systems.
So I guess Fredrik, you'll start.
Yeah, so what is Arriver? We're a software company owned by another company called Veoneer. We produce software for vehicles, camera systems in vehicles that detect lane markings, road vehicles, pedestrians, and so on, so that the cars can automatically brake or steer. You probably know about Tesla Pilot and that kind of system. So we develop the same kind of software and sell it to Veoneer, who integrates it into the hardware, as you can see, several of them over the years, and sell them to the car manufacturers. So you can see a few of the cars, Polestar, Mercedes cars, and other brands that we have sold to. We have offices in 5 different countries, are around 800 people in Arriver developing this code base.
All right. Yeah, first of all, we want to give you a small recap of where we came from and where we're going, where we're heading. So we have a vision at Arriver that tests, we try to run them as early as possible, since, of course, the cost for bugs, they increase exponentially with detection time. So we try to always shift our tests to the left. I think it's a expression that everyone recognizes when you use Bazel. We strive for a commit time of 10 minutes. So we want to be fast. We want to have a quick response time. I think we have heard it multiple times. It's very important. So actually, that was a goal. We didn't know if we would reach it, but we just said 10 minutes, that's enough. The only version of the code base we want to maintain is the master version. So we want to do all our development there. We want for it to always be stable, so we always can deliver from it. That is the basic concept. And of course, after 10 minutes, we should basically know that everything works. And when things are past gate, we don't want to find more errors. Of course, we do find errors, but then our goal is to kind of create a small reproducer test that you can run early in the pre-checks. So the pre-check tests are so extremely important in this to make them fast, so we have an extremely fast response time. But where did we start? Well, I guess we started where everyone else started. We had multiple build systems, and everyone could decide whichever build system they wanted to have. There was an extreme overhead for code reuse, because nothing was the same. Our pre-submit tests, we're still using Zool, so we do have these speculative merges that kind of orders things before it comes into the software branch. But the tests there, they ranged from 50 minutes to 3 hours. So since everything is decided by the longest time, we had an extreme time for the pre-submit checks. And the integration time took days. We thought it was unacceptable. So this complex submodule, and we had also this really complex submodule structure. So that led to that we had version conflicts and interface breaking changes. and people avoided basically all kinds of code improvements and refactoring. And of course, it is possible to check that your change was working everywhere. So what did we start with? Well, the first thing we did was to Bazelify everything. I mean, then we could use and show the developers that, okay, this system has potential. We started also then to introduce remote execution from the start using BuildBarn. And there the developers got the look and feel of what it could be. But the integration was still done with binary deliveries. It was still extremely slow. So the second step would be that we still keep our multi-repository structure, but we flatten it. So we have created a small, an emulated monorepository that is standalone from Bazel, that kind of emulates, for the user, it looks like you are in a monorepo, but from the in the backend, it's many Git repositories and many artifacts. It doesn't really matter. We're using Gerrit, and they have a functionality there, which is called submittal topic, where you can tag your changes so they belong together, and we submit them together. And now we achieved the end goal. We had fast integration. Still, if we keep the submodules, Gerrit still have a pain to merge changes. So the third and last step, the small, would be to remove all the submodules, inner submodules. So we only have the flat submodule tree left, and that's currently where we are at. So if we go through this development flow, we have this standalone monorepo emulation that consists of about 100 Git repositories. We have artifacts that we fetch from an external artifact service. Also, the build environment gets downloaded. Everything that we need for the monorepo emulation itself is downloaded. So we are actually totally hermetic. We don't depend on anything from the local environment, neither on Windows nor Linux. We both have Linux and Windows in our setup. So everyone knows that Windows is a pain, but we do have it. We build then our source code with Bazel, and we use BuildBarn, where we have both hardware workers, where we have dedicated hardware, so we can actually run hardware tests directly using remote execution, and also generic Linux workers. So if we go to some statistics, so of course remote execution is everywhere, accessible for everywhere in the world. We do have local cache servers, so when people using remote cache, it still goes fast. On Windows, we only have remote cache, so that's why we have local cache servers. The check-on times, thanks to this, and that we could reuse the monorepo, we could decrease the checkout times from 30 minutes to about, most of the cases is around seconds, so around 10 seconds. If you have recursive states, I guess 2 minutes is what we allow it to wait. And we could decrease our pre-submit times from hours to seconds. And then minutes to integration test. We can do a hardware test within 10 minutes. So we have run a full hill simulation within 10 minutes. And of course, the license, the pain of license is always running short. That is totally gone. I mean, the remote cache, you seldom rebuild anything. Perfect. And of course, set up for a new employee to struggle with all the licenses, all the license files, or whatever system you're using, or the compilers you need to set up, whatever. It doesn't, no need. Everything is contained. We are actually thinking of open sourcing our monorepo emulation. It's in the start, so don't hope it will be out soon. But if anyone is interested, I guess you can notify us if we should speed up the process of it. So this monorepo is, of course, pretty scalable. And by design, Ed did a very good work when he designed BuildBarn. So also that is extremely scalable. I think there are some upsides using an emulated monorepo emulation, and that is that we can actually have individual permission management for each repository. If you have a monorepository, we have to have the same permissions for the whole repo. Anyway, if you use a Git repository. But if we have multiple Git repositories, we can have, for instance, an interface repository which is shared with customers, or we can have customer code bases, which doesn't automatically share the whole core component, all the core components. And remote execution, of course, everyone can use the same. We think it's secure enough for everyone to use the same remote execution service. Okay, so upon this, we have the pre-submit tests. We do also have something called confidence level, CL. And the CLs is an increasing response time. So we have actually 6 stairs, you can say, where we have an increased feedback, but also an increased quality. So gate, 10 minutes requirement, post, also the same. Here we run every commit. The hourly test, we get response of many other, the hill test or feature test, as we call them. And the nightly and weekly, where we can host the performance statistics. We can then set up several of these pipelines, so we can have multiple of these monorepo emulations using the same submodules, but maybe a different constellation of them. So we can actually trigger them from our main pipeline and have custom projects working on the side of it and have their own separate confidence level staircase. What happens if anything goes wrong? Well, then we have this, what we call the automatic git-bisect. So good name. Well, when something goes, in our case, yellow, we start the automatic bisect. And when we get bisected which commit is wrong, we notify the user or the team, and we do some kind of visualization for it. Our end goal is, of course, that everything should be green. We do have time requirements that you have to fix your commit within a certain time, and if you feel that you can't, then you have to revert it. We have not introduced automatic reverts, but maybe inspired by the previous talk, we will. So the end goal is that we always have a green state in our confidence levels, and of course, then we have something that's ready to be released. We can still do manual testing. I mean, this is just continuous delivery to make sure that everything is working all the time in the repository. It doesn't mean that we've done a full release. There's still the release process after this. But the point is that everything we detect later on, it has to be fitted into this staircase. And if we find a test that can be run earlier, let's do that. So here is where we switch.
So Andreas had talked about our emulated monorepo, and we have then branch following, that submodules always are up to date using Gerrit's branch following feature. We also have a cross-repository changes made available using Gerrit's submit whole topic. And we have had to patch Zool to be able to cope with these topics as well. In our emulated monorepo, it's basically a top repository where all submodules are placed in a modules directory, and the Bazel workspace name is used as a submodule name within our top repository. And as Andreas said, we have removed all inner submodules. But it was a very simple transition there where people could build both in the original repositories and from the top repository using the Bazel repository naming. Confidence levels, easy to move tests. We have automatic git-bisect. We also filter out infrastructure errors and notify, well, me and Andreas, so that we can fix them quickly and make sure that the developers have focus on the actual code errors and do not have to think about anything else. Bazel is used, and as we said, we download all the tools, no installation needed, not even Python. And that also eliminates any errors with tool conflicts from different users installing different versions, for example, of different tools. BuildBarn is used with 600 threads on Linux, but and we use it on our target hardware as well. For Windows, we only use remote caching, but we also use Wine on our Linux remote execution workers in some cases. We have a 5 terabyte cache, and well, it lasts a few hours. Also use BB Client D, or starting to use it as of today, to cope with, or to reduce the amount of data we actually download, especially when we run Bazel coverage. So far everything is good, but what's next? We have achieved down to 10 minutes now, but even with 99.9% cache hit, we don't get it even faster than 10 minutes. So what is happening? It turns out that Bazel is a bit slow for us, and we also have flaky hardware tests, which doesn't help. So we need to optimize Bazel to get any further down, say if we want to go to 1 minute. And one example is that when we run a certain build with, it can take 30 seconds to do the analysis of the build.bazel files. In this case, we have 50,000 targets configured. So can we reduce this analysis time? We have the problem that the analysis cache is discarded because we changed platform. Say sometimes we run debug, sometimes release, sometimes we run for a certain platform, sometimes we build for another platform that we have. And that discards the analysis cache within Bazel. One way to keep the analysis cache would be to distribute so that each platform we build for is built on individual servers. But that would be pretty difficult to maintain such a such build service. We would like, well, it would be optimal and speed up things drastically. But the easy way that we do is that we run Bazel with Starlark CPU profile to be able to profile all our Starlark code, and we'll work on it. It's pretty hard to get further there. And we're the execution phase. And after profiling that, we can see that a lot of CPU time is spent on merkletree.build here. Then we also have network latency when we're checking for cache hit and download outputs. But it turns out that this Merkle tree building is very expensive when you have lots of inputs. For example, if you use Booz C++ library or whole GCC tool chain to put in there. And you can see that the Merkle tree is part of the remote execution API, according to the reference here. And it's needed both when executing, but also when checking the cache. If you want more details about these profiling results, you can see the Bazel GitHub issue here. So how can we fix that? Well, I created a patch where I calculated a fast hash, which is done by memorizing kind of the structure of the depth set, the structure of all dependencies within our build structure. And that then all those hashes can be memorized, and well, the calculation gets a lot faster, as we can see in the example here, that when it's optimized, it kind of almost vanishes, this cache calculation. Then I do a check of that fast cache, see if I have a hit, or I translate it into the full Merkle tree hash, and then I have to check for cache hit there, and then I need to download, and then but we have a lot of latency left. So after also implementing an in-memory cache, I remove all network latency. We can see that all these small bits and pieces here is kind of the fast cache calculation. But there is a lot of stuff left here. So also to note that the in-memory cache is totally, well, doesn't help if you just parallelize lots of jobs, but it helps to investigate what the problem actually is. So there's a lot of things outside this part of the code base that is taking a lot of time. And this is when you have a cache hit. We assume that these parts are kind of linearly scalable on the number of inputs that you have for an action. And if we can employ the header scanning, the include header scanning that Google actually runs internally, if we can use that, we have a measure that we can prune the inputs by 75%, and hopefully all these extra time can then be reduced with that amount of time. And otherwise, we are kind of stuck on ID. So that is our next step, to actually try to get this include scanning connected and implemented within Bazel. The code is there, but it's not in Bazel, not running with Bazel by default. If anyone else have any idea how to actually reduce all this time, it would be, please reach out. In summary, we have managed to reduce time. Well, it's actually a factor of 20 if you think about 3 hours to 10 minutes, but it's an enormous factor if you think about 1 week to 10 minutes. And monorepo emulation, as we described, and we can therefore have access rights on different repositories. We use Gerrit and Zool to merge our commits and make sure that master never breaks. Bazel and BuildBarn with automatic git-bisect when we run our periodic tests. And one big benefit of all this work is that nowadays everyone works the same way, because all our tooling, the tooling that we have developed, is very smooth to use, it's very simple, and it's very fast. So there is no need for any developer to invent any other way of developing. But if we want to get even shorter times, we need to reduce the analysis phase, reduce the execution phase in Bazel, and fix our flaky hardware tests. And that's it from us.
Well, thanks a lot, Fredrik and Andreas. That was a really insightful talk. I think that's also demonstrated by the fact that so far this is a talk with most of the questions coming in from the audience. So that's pretty good. I'm first basically going to run over some questions that you've already answered, just to make sure it's good to skip. So first of all, are you using BuildBarn with Windows workers? And I think you've answered that already. Namely, you're only using remote caching for Windows, or you're using Wine in combination with remote execution. Is that right?
Yes, that's right. So yeah. Actually, we have, therefore, we run Bazel on Linux, and we have Windows actions that we run when running Bazel in Linux, and then our actions are built up using Wine then. So people can run these actions actually also locally in the Linux environment. So the whole build chain from source to the final product needs to involve both Linux compilers and Windows compilers, but it's solved using Wine basically. Oh,
that's pretty slick. Yeah. So also one question that you effectively answered was, are you using builds without the bytes? And I think the answer to that is, well, you're switching to BB client E. So I suspect you've either experimented with it or are past that point, right?
Well, we are using it. We are experimenting, but when we do Bazel coverage, we need to do download all, and that's why the BB client D comes into speech, because well, it's gigabytes of downloads, many gigabytes of downloads for our coverage run, and we would like to avoid that. And if it works, turns out to work well, I'm sure you have implemented it well, Ed. But if it turns out to work well, then we can employ it with all the other builds, not just the coverage.
Okay, well,
Have
let's
some
hope
kind
for
of
the
testing period left.
Sorry, what's that?
We have some kind of testing period left.
Okay, yeah. So the question that actually got most of the upvotes was, could you elaborate a little on how you emulate a monorepo? Can a single PR span multiple repositories? Would it be reviewed, tested, and applied as if it's a single atomic change?
So when you work on so we have a top repository with the modules folder, and inside that we have all the sub modules. So when you want to span multiple repositories, you have to create multiple pull requests or changes in Gerrit as we use. So it's not a single pull request, it's multiple of them. But then when you add a topic in Gerrit, Gerrit will make sure that all these commits will be merged atomically. Then Gerrit has this branch following that if you in your .git modules file write branch equals period or any other branch name, then Gerrit will also update all the submodules pointers. So we get an atomic commit in all the repositories and atomically an update in the top repository with all the submodules pointers in one step.
Okay, that's that sounds pretty slick, and I think that also answers it really well. So let me take a look at like the next question with most upvotes is the monorepo emulation specific to Gerrit, or could it also be used in combination with GitHub?
I think you would have to develop some other chain around it. Say you would have to merge things yourself and then push the merges up to the master branch. I'm not. You would not be able to do this atomically though. So, well, you will have to do all that tooling yourself.
Yeah, exactly.
Maybe it's of interest. Maybe it's of interest to do that, and there should be someone actually doing it for the whole community.
Mm-hmm. Well, to ever ask that question, here's your chance to also build something similar for GitHub. Yeah. So going on to the next most popular question is, previously it has been mentioned that the analysis cache can be stored remotely with changes to Bazel. Is this something you have considered?
That's nothing I've heard about. That would be very interesting if we can store the analysis cache in some way.
Yeah, if I understand correctly, I'm not an expert on this topic, is that at least within Google, they sort of have a distributed version of Skyframe where like parts of Skyframe's graph and data can be stored remotely and queried. Yeah. Okay.
It would be nice to store it and then retrieve it when you run the same kind of command again, because it's just this discarding that is problematic.
Yeah, exactly. Yeah. And now, did you compare Git submodules against something like Android's Repo tool? If so, what made you pick Git submodules?
Yeah, maybe Andreas have
legacy. I guess it's legacy. I mean, we had it previously and we needed to migrate. So, I mean, some kind of a migration process had to take part, and so we used employ the same system. That, I guess, is the basic answer. Okay.
So there are two more questions left, and we've got 9 minutes till the next talk starts. So I really want to get both of them asked. So the one with most upvotes is, do you auto-scale BuildBarn workers? And
no,
if so,
we don't.
how?
No.
Okay. Yeah.
So we have 600 workers, Linux workers, but threads, whatever we would like to call it. But we, on average, I think if I just look at the graphs, we use 100 of them. But we do peak and we do get a queue every so often.
Yeah, exactly. Also, as the offer of BuildBarn, in case you want to do auto-scaling of BuildBarn workers, one of the easy things you can do is you can use certain metrics that the scheduler exposes and use that to, what's it called again? Use, for example, if you're running on Kubernetes, use the Kubernetes custom metrics API to create like a horizontal pod autoscaler based on those. So
now we run all these in-house on our own servers, so we don't really have any use of the servers for any other use case. So we don't have to scale them down because no one else wants to use them.
Yeah, exactly. Okay, thanks for answering that. And then another question: could you share how big your source code is approximately?
Oh, do you have any numbers, Andreas?
I don't know. No, I guess hundreds of thousands, around 100,000 lines of C code. I don't know. It's somewhere there.
We have no clue. We haven't counted.
It's big.
Yeah, well,
yeah.
It's a big legacy. I've worked here for 11 years, and with hundreds of developers, you get a lot of code.
Mm-hmm. And that was just the source code, I guess. There's tooling around it, and it's multiple repositories.
And the final question that was asked, and that was actually a question that I had asked, was so you mentioned during your talk that I've observed this as well, that a large part of the slowness in Bazel is actually computing Merkle trees, right? Bazel spending most of its CPU cycles computing SHA sums, right? It's solving a SHA puzzle. So you mentioned that you proposed adding some kind of like a faster hashing, or like a fast hash that you could use to like query the action cache more efficiently. But one of the questions I had, and maybe this is a bit of like a too complex one, is do you maybe also think that this is sort of like a design flaw or incompatibility between like Bazel's top half and remote execution, where there's this constant conversion, like going from Merkle trees to lists or sets of files? And could some of the like this redundant recomputing of SHA sums also be prevented by sort of pushing down the Merkle tree deeper into Bazel's data structures? That like it, instead of it just being about sets of files, that it also thinks about a directory tree structure where SHA sums are annotated. Would something like this also address it?
Well, I think it would be pretty hard. You have the structure of your code with in our case, CC libraries that depends on other CC libraries. And I think it's the way I would like to solve it is instead that each CC library calculates its own hash. And then you build a tree of this and upload that hash into as the input hash to BuildBarn. And then the remote execution side, that has to resolve it into a list of files. Because checking the cache will be very quick, because everyone computes the same, everyone has the same structure if everyone uses the same build system. So the hash will always be the same, even if it's not deterministic between versions of Bazel. So checking will be quick, but then when you execute, you need to convert it into a list. But
yeah, exactly.
That's just a one-off computation. So let's just push that Merkle tree into the remote execution side. You will remove that. But note that it's just, for our case, it's just 30% of the build time. I thought it would be more, but there is a lot other things going on around it, unfortunately.
Yeah, exactly. I've observed that it also becomes worse if like SDK dependencies, that kind of stuff also becomes bigger, right? Because then the size of input routes tends to become bigger and it all becomes slower. So we'll have time for one more question regarding the size of the source code. I was mostly interested in the size in bytes, actually, not lines of code. Sorry about the confusion.
Yeah, Andreas, is it 10 gigabytes that we check out or something?
It is. It was much larger, but we cut it down.
So we have moved some, is it like 20 gigabytes into the Bazel remote repositories, like HTTP archive and so on. So 10 gigabytes in the Git repository and 20 gigabytes in HTTP archive.
Okay. that answered it pretty well. I would like to thank both of you for giving this talk. It's been really interesting, and it's given like a good overview of like what kind of infrastructure needs to set up to build large projects, right? It doesn't tend to be simple, unfortunately.
And soon you may actually have used this code may be in your car in a soon future.
Well, I hope so. I still need to buy one. Well, take care.
Thank you.